Hello all. Oh, in this video, I will discuss about the mathematical modeling of a TC machine and we will model the time domain model of the TC machine in MATLAB and SIMULINK. So to model the DC machine, we need some mathematical equations of the DC machine, which are on the screen. We can take a screenshot because we need these equations in our SIMULINK model. Here the first equation gives the information about IA, which is the armature current, and the second equation gives the information about IF, which is the field current, and the third equation gives the information about the torque speed relationship. And this EB and TE relation also equally important that we need in our modeling. So moving to MATLAB and SIMULINK. This is the SIMULINK workspace where we have to draw the model, and we have to go to SIMULINK library browser to get the required blocks which we will use in the modeling. So we have to inside the model we have to use some subsystems to define our armature and field and the torque speed relationship. Then we'll interconnect those three subsystems to get our overall system. So first of all, let us model the armature. So we will take the help of blocks under this commonly used blocks. I'll take the help of input. So right click on this, then add to the untitled, that is the workspace name. Then I need output port and I need scope. I need this sum block. I need the multiplexer. I need an integrator. And under the user defined functions, we need this function. Okay, so now separating all the blocks. By double clicking in this sum block, let us change the icon shape to rectangular for a better visibility purpose, and then change this one as the three input ports, that is plus, minus, plus. Apply. Okay, now let us enlarge this one. Yes. So this input one, let us rename it as armature terminal voltage VA. Connect it. Now let's connect it and then we'll understand. We need another two input ports, so right click and drag it, paste, so it will get copied. Let us rename it as omega and IF. So by this omega and IF we can get the relationship of EB, the back EMF, that earlier we have seen in this, that EB is equals to K into omega into IF. To get this relationship we are doing this part. So now another user defined function block I need, also another we need in to get the I into RA, so another one. And now let us multiplex these two inputs, then the output will be go to the function. So here we have to define the function, that what kind of mathematical calculation it is going to do we have to double click on this. Now we have to multiply WIF and the K value. Suppose we are taking the K value as a constant value, that will be equals to 1.2. U of 1 multiplied by U of 2 into 1.2. So that output will give us the back EMF value that we are going to subtract from the VA value. Sorry, here I have to do this as minus. So again, let us double click and change it to minus. Apply. Okay. Then I have to write the mathematical function here also, because after doing this part I have to divide this part with the armature inductance. The armature inductance is given in the question itself. So suppose here in my example it is given as 0.086. Let us make it as the input U divided by the armature inductance 0.086. Now apply. You can see that whenever I am applying, I can see the text here, the function. Okay. Then this integrator part will do the integration of the whole output of the function block. Then it will give the output as IFA. So here actually another thing we have to subtract from the armature terminal voltage and back EMF to get the IA. So that function is IA into RA. So IA is the armature current and RA is the armature resistance. We are taking the armature resistance as given in the question. It is 4 ohm. Now I have to define the function as input U into RA value, that is 4. Apply. Okay. Now I have to connect this to IA, and the output will be subtracted from the VA value. Now we don't need scope here. Maybe in the next module we need it. So let's keep it aside. Now we have completed the modeling of the armature current. So now just we have to select all, right click on the selected portion and create subsystem from selection. So now we successfully created a subsystem for armature current. So let us remove all these ports. So I don't need that. Okay. Now I have to create another 2 subsystems like this, for one for armature, one for field current and another for torque speed relationship. So let us model the torque speed relationship. Then we will move into the field current. So again, to model the torque speed relationship, we have to go to the library browser, and then under commutative loss we have to select input, output, sum block, integrator, and then multiplexer. And under user defined function I need a mathematical function which is to be user defined. Okay, now separating all the blocks. Sorry. Okay, now by double clicking the summer block, we can change the shape as rectangular shape. Then we can add another input because we need 3 inputs, so it should be minus, plus, minus. Okay. Input is there. That input will be the load torque. Here the output will be the speed omega. We need the multiplexer. Another 2 input ports we need. Another 2 mathematical user-defined functions we need. So this, let's rename it as IA and IF. We have to multiplex both of them and give to the input port of the mathematical function, write a mathematical function to get the electromagnetic torque equation here, that is T is equals to K into IA into IF. So to get that, let us write the function U of 1 into U of 2 multiplied the K value we have taken it as 1.2. Apply. Okay. So another output port I need. Let us rename it as T, electromagnetic torque. Kinetic. We have to add the electromagnetic torque to the input. Now we need actually we are modeling this equation number 3, so we are done with the T and TL part. Now we need B and B into omega. Then we will go to the divided part, that is the J. So to get the omega into J, we have to define the function as the input omega into J value. It is given as B, it's B value, that is 0.0081. Apply. Okay. So the input U is omega and the output will be subtracted from the TL minus T. And this function will be, so we have to divide with J. So the input is U and divided by J value, it is given that 0.017. Apply. Okay, so we are done with the speed and torque relationship subsystem. So now, okay, let's connect this scope. No, we don't need here any scope. So let us select all, right click, create a subsystem, and let us remove these input ports. Now I have to create another subsystem for the field current. So similar process. Go to library browser. We need here user defined function, so add it to workspace. Then we need input port, output port, sum block. We need an integrator too. Okay. Now let's separate them. Okay. So double click on this block, make it as rectangular. We need here one plus, another minus. Apply. Okay. Here output, in the output will get the field current value, so that is IF, and in the input we are giving the field voltage VF as the input. And here if we look into the field current equation, that is IF equals to this one, that equation number 2. So we have VF, we have to subtract IF into RF from VF. So to do that, we have to use another user defined mathematical function. Make it as U into the RF value. It is given as 370 ohms. Apply. Okay. Then the input will be IF and the output will be subtracted from the VF voltage value. And we have to divide it with LF, the field inductance value. That is U divided by LF. We are taking as 6.4. Apply. Okay. Now select all. Right click, create a subsystem. Remove these input ports. Yes. Now we need another scope. Yes. So in one scope, change the settings, that change the input ports to 3, because we need to see this omega, IA and IF in one scope, and in another scope change the input port to 2, because we need to see that that load torque and electromagnetic torque at a time. So let us make it to here. From here, by double clicking this one, you will get this type of window. Just go to these parameters, then number of axes, change it to 2. Apply. Okay. Now just enlarge this one, and by double clicking this scope, we will go to the parameters, change the number of axes, that will be this 3. Apply. Okay. Yes. Now we need the VA value. Let us, as it is given in the question, to take the 220 volt as the armature terminal voltage. Let us go to the library browser. From the commonly used blocks, we can get the constant, this block. So let us add it. So we have to rename it as VA. Double click, constant value, give it as 220, apply, okay, connect it to VA port, and I have to connect to omega to omega, IF to IF, we need VF also, this 220 volt, so let us connect it to this one, and IA to IA, we have to connect it. So let us take another constant block, rename it to load torque, keeping the load torque as constant. That let us take a value as suppose 2.5 Newton meter torque, apply, okay, so I have to connect this load torque to and IF to IF, then we have to see the torque, electromagnetic torque characteristics with respect to time, because it is a time domain analysis. So every parameter that we are going to see in the scope, that is the electromagnetic torque, load torque, and the speed, armature current, field current, that will be with respect to time only. Here we are going to see the load torque. Now in this scope we are going to see speed, IA and IF. I think we are done with the modeling part. So let us save it, Control S, save it as DC, save it. Now we have to simulate by clicking this run button. Let us simulate and see what happens. Yes, it is done. Now by going to the scope we can see the characteristics. So here I am going to the scope 1. Yes, by doing the auto scale, it is the auto scale button. You can see the graph with respect to time. This is the electromagnetic torque graph. We can zoom it by we can zoom the x-axis from here. Yes, this one, and we can zoom also the y-axis by clicking this button like this in an auto scale. So this is the constant load torque we are giving as 2.5 Newton meter. And in this scope we will get three axes, that is one is omega, one is IA, and another is IF. Let us auto scale. Yes, negative like this. We can zoom this we can zoom these graphs and we can study those values, if it is coming correct or not. We will calculate in a pen and paper and we will see whether it is coming correct or not. Okay, that's all about the time domain modeling of the DC machine. Thank you for watching.